Here is an example problem on Swinburne's test. I think this is a very illustrative problem, and it will actually clarify a lot of your concepts on machines. So this problem I have actually got it from a book. Okay, so this is example 7.57 from Electric Machines. This is the name of the textbook. And this is fourth edition, and this is by Nagrath and Kotari. So Kotari and Nagrath are the authors of this book, and this book covers a lot of other machines also, and this one is specifically for this particular Swinburne's test. So anyways, you can just go through the question once and try to understand what is there in the question, and from that you try to solve this particular problem. Meanwhile, I'll go through the solution. You can pause the video now. You can just give an attempt how you can solve this problem, and we'll continue on it. Okay, so let's continue. So here, first question that is given is determine total constant losses of the machine. So this is constant. So how to find constant losses of the machine? So constant losses, you know, is the shunt field losses. So for that, let's first find out what is the shunt current. So if you look at the, so in the title motor is given, so let's draw it as a motor. So the same machine can act as generator and motor, as you already know. So this is depending on the connection. So this is now connected as a motor. So 250 volts is the supply voltage, and this is 0.8 ohms, and this one is 275 ohms. So now I have the voltage and I have the resistance, so I can find what is the current in the shunt field winding. So ISH is nothing but 250 divided by 275. So this one comes out to be, so let's use calculator, 250 divided by 275. So 0.909, so I can approximate to 0.91 amperes. So I know the shunt. So what are the losses? So shunt copper losses, I'll denote as PSH, ISH square RSH. So that's nothing but 0.91 square into 275. So I'll just square this and then multiply it with 275. So 227.27, or I'll just round it off to 227.3 watts. So first step what I did is calculated the shunt copper losses. Now how to find the iron and windage losses? To find the iron and windage losses, first I should know what is the copper loss in the armature. So for that, here the current is 0.91 amperes. That is given the question, and that we have just calculated. And given in the question, it takes 3.91 amperes. So 3.91 amperes is the current flowing from the main line. So therefore, since this is a motor, so this is 3 amperes. So IA is nothing but IL minus ISH, so which is nothing but 3 amperes. So once I know this current as 3 amperes, I can calculate the losses in the armature and then find finally the losses. So that actually we are calling it as rotational losses. So P rotational losses. This is nothing but earlier we called it as iron losses plus friction and windage losses. So all this, nothing but rotational losses. So that is nothing but 250 volts into 3 amperes minus 3 square into 0.8. So this is the total input to the armature, this is the armature copper loss. So then from that I will be getting the rotational losses. So let's use a calculator. 250 into 3 minus this one. So 742.8. So this is the loss that we are getting for the this one. So now I have the losses in the armature, and I have the, this is nothing but, okay, so this is armature losses only this part, and this part is the total losses. Okay, so now I have this. So from this I can also know what is the constant losses. So what are the constant losses? Constant losses are nothing but 742.8 plus 227.3. So plus 227.3. So this is about 970 watts. So this is the constant losses of the machine, that is 970 watts. This solves the first part of the question, determine the constant losses of the machine. This one we have solved it. Next, what is the machine efficiency as a generator when output of 10 kilowatt at the rated voltage and the speed? Okay, so now machine is operating as a generator. So let's draw the diagram. So when the machine is operating as a generator, G, that means there is a load here. There is an electrical load, and then there is a shunt field winding here. So this is the load, and load voltage will be there. So output of 10 kilowatt at rated voltage and speed. So this voltage is anyway 250 is the rated voltage. This is 10 kilowatts, and the rated speed is also there. And we already calculated this is 0.91 because this voltage is 250 volts and this is 275 ohms. From that I can calculate this current as 0.91. Now what is with this current? The current that is going to the load, I load. So the current will be 10 kilowatt divided by 250. So load current is 10,000 divided by 250. So this comes to 40 amperes. So this current is 40 amperes and this current is 91.91 amperes. This is the shunt field current. So therefore the armature current would be 40 plus 0.91. So this is the armature current. That would be IA. So here IA will be IL plus ISH because this is a generator. So 40 plus 0.91. So of course it will be 40.91 amperes. And we know this is 0.8 ohms, the resistance is given. So therefore the variable loss. So the variable loss is IA square RA. So that is 40.91 square into 0.8. That will be, so 40.91 square multiplied by 0.8. So 13, so 1339, I wrote it off to 1339 watts. Now I know the variable loss. And what is the constant loss? Constant loss we already calculated in the earlier problem, that is 970 watts. So constant loss is 970 watts. So this is from part A. So total loss will be 9 and then 0, this one, 2309 watts, and therefore and the output is 10,000, that is 10 kilowatts already given. So therefore efficiency will be output by input. So that will be 10,000 divided by 10,000 plus 2309. So that will be my efficiency. I am working as a generator. So 10,000 divided by, I open the brackets, 10,000 plus 2309. That will be 81.24%. So this is how the Swinburne's test is helpful. So this is part B. So let's go back. So what is the machine efficiency as generator? All these things we have solved. Now let's look at part C. What is the machine efficiency as a motor with input of 10 kilowatt at the rated voltage and speed? So now let us solve the part C of the problem. So part C as motor. So let's draw the diagram of the motor. This is a shunt machine. Now if I keep M, it is a motor. Now the motor will have electrical input. So there is a voltage source here, and this is 250 volts because rated voltage is already mentioned. And this time the input power is 10 kilowatts. So therefore this current 40 amperes will be the IL flowing from this to this. And this current already we had calculated, it will be 0.91 amperes because this is 275 ohms. So 250 by 275 is 0.91. This is the ISH. So therefore the IA will be what? So applying Kirchhoff's current law at this point, so IA will be IL minus ISH because this is a motor. So 40 minus 0.91. So 40 minus 0.91 is 39.09, or let's call it 39.1. So this 39.1 and this is 0.8. So now I can find what is the copper losses. So 39.1 square into 0.8 is what? So this I will square and multiply it with 0.8. So this 1222. So 1222 watts. I got this is 1222 watts is the iron loss. Sorry, the armature copper loss, or it's the variable loss. And what is the constant loss? So constant loss again 970 watts if you remember. So we have the constant loss also. So the total loss will be 2192 watts. This is just the addition of variable and constant losses. So, and we also know the input, because it's a motor, input is 10 kilowatts. So now I have the losses and input, I can find the efficiency. So efficiency is input minus losses divided by input. So let's do that. 10,000 minus 2192. So 7808. So basically this is, or 78.08%. So like this I can calculate the efficiency of the under the motor conditions. Okay, so this solves the C part of the question. Now the next one is, what is the maximum efficiency working as a generator? Alright, so again you can try solving this. So So this is the D part of the question. Maximum efficiency as generator. So now you know that condition for maximum efficiency is nothing but variable loss should be equal to, I'm sorry, variable loss. So this is the condition. So let me like this, constant loss. So this is the condition that is required for this one. So therefore, the constant loss already we calculated is 970 watts is the constant loss. So therefore, what is the variable loss? So variable loss is nothing but Ia square Ra, that should be equal to 970 watts. So therefore, from this Ia will be nothing but square root of 970 divided by 0.8 is what we have to calculate. So let's go back here. So 970 divided by 0.8 and then the square root of that answer. So 34.82 is what I am getting. So this is 34.82 amperes. So as long as the armature current is 34.82 amperes, the efficiency will be maximum. So now under the generator operation, again you know that armature current minus shunt current is nothing but the line current. So therefore, 34.82 minus shunt current is 0.91 as we already know. So that will be minus 0.91, 33.91. So this will be 33.91 amperes. This will be nothing but the load current. And the output will be IL into V. So that is nothing but 33.91 and rated voltage is 250 volts. So that will be multiplied by 250. So 8477.7. So 8477.7 watts. So at the time of operating as generator and when the output, electrical output, because electrical for generator output is electrical. If the output of the electrical output of generator is 8477.7, that corresponds to maximum efficiency. And what about total losses? Total loss is nothing but 970 plus 970. Constant and variable both are equal. So that will be 970 into 2. 1940 is the losses. So under that conditions, the maximum possible efficiency working as a generator max is nothing but output 8477.7 divided by output plus losses. So how much is that? So 8477.7 divided by, and I open the brackets, 8477.7 plus 1940. So 81.37 or 81.38%. So this is the maximum possible efficiency that can be achieved with this particular machine when working as a generator. Now again you can consider it as working as a motor, and then also you can try to solve it. In fact, that is what is the next part of the question. So I have actually run out of space. So let me make some space and then I try to solve it within that. In fact, I'll remove this. So yeah, so let's let's choose a different color. So now when working as a motor, for some reason I am not able to erase this. Anyway, so when working as a motor, so we already know that what is the armature, the line current. So line current will be armature current minus shunt current. So that is we just calculated the armature current to be, I'm sorry, line current will be armature current plus shunt current, because that is the current which we have to use input. So it will become 34.82 plus 0.91. So that will be how much? 34.82 plus 0.91, 35.73 amperes. So under these conditions, what will be the input to the motor? So input will be 35.73 multiplied by 250. So that will be multiplied by 250. 8932. 8932.5. So therefore efficiency maximum working as a motor will be input 8932 minus 1940 divided by 8932. So minus 1940 divided by 8932 again. So 78.28. So this way we are getting the two different values of maximum possible efficiency, once when operating as generator, others when operating as motor. So with this problem, I hope you got some idea about the entire concept of the Swinburne's test. It's a test which is done on no load, and by testing the motor on no load, we are able to estimate the efficiency of the machine at different loads. Now, some of the disadvantages of Swinburne test is that in this test, the temperature rise of the machine is not considered, the effect of temperature rise of the machine. Because we are doing the test under no load condition, so we don't know how the temperature rise will change the behavior, the parameters of the machine. So therefore, it is not that accurate as compared to actually loading the machine. Also, the measurement of armature resistance and measurement of field resistance is done under the normal conditions. That is under the cold, like it's a cold resistance that we are measuring. But when the machine is under operation, its temperature will increase, and so will the armature resistance and the field resistance will increase. So that again will give some error in our calculation. Therefore, you should be careful when you are doing Swinburne test. See, for example, here the armature resistance of 0.8 ohms is given, but is this 0.8 ohms measured considering the rise in the temperature of armature or not, is what we should consider. So that is one more disadvantage. This one. So with this, I think we'll complete this topic, and let's go to the another test on this DC machines. Having discussed Swinburne's test, now let's come to the third one, that is Hopkinson's test. So this Hopkinson test is another test on the DC machine, and this is done on two identical machines. Hopkinson's test. So this is what is called as a regenerative test. So the meaning of this regenerative test is that whatever the power that is taken is again generated back or given back to the supply. So that's why it is called regenerative test. So basically only the losses are consumed from the supply. So this regenerative test, only losses are consumed from the supply, whereas the machines are fully loaded. So this is done on two identical DC shunt machines. So one acts as motor and the other generator. So basically what happens is that, see, this is a motor, it takes input is electrical, and then this is generator. So the output of the motor is mechanical. So electrical energy is supplied to the motor. Motor generates the mechanical energy. That mechanical energy is supplied to the generator, which in turn generates the electrical energy, which is in turn again supplied back to the motor. But just that you need to supply extra losses. So this is the main supply. So the main supply supplies losses to run all these things. So this is what is the very brief diagram of the Hopkins test, but then a detailed circuit diagram I'm going to draw and we're going to discuss that. Okay, so just to make your understanding better, I have drawn this circuit, but let's see how we are going to achieve this kind of a connection. So, so I'm just drawing two lines like this. So basically this is the positive line and this is the negative line. So I'm just actually connecting the supply here. So let's call it as V main. Okay, so this is the main supply. So whatever is the voltage that is rated of these two machines, that I have to supply the main. Now, first let's talk about the motor. So there is a motor. Now, in order to measure the current going into the motor, I connect an ammeter here. And this motor also requires a field winding, so I am connecting a field winding here. Again, in order to measure the current in the field winding, I have this. Also, I would like to be able to control the field winding current here. Then that is why I have introduced a variable resistor. By changing this variable, you see this is completely independent of this. So this branch is having this voltage of V main. So if I increase this resistance, the current will decrease. So that way I am able to control the current. So let's give some notation. So let's call this current as IFM. So this is the current in the field winding of the motor. Similarly, this current, let's call this as IAM. This is the current in the armature of the motor. So imagine this is the situation. I just, of course, we require a starter to start the motor. I cannot directly connect this to the main supply. But then if I do this connection, then I can imagine that the motor is running on no load, and the output of the motor is the shaft, and which is running at some kind of a no load speed like this. But then the mechanical power output is zero because there is no load connected here. Now I'll introduce the generator. So the generator G is mechanically connected to the motor. So to measure the generator current, I'm introducing an ammeter here. And then here I just do this kind of connection. This is a switch S. So this switch S is open at the beginning. Okay. So therefore the generator ammeter current is zero because there is no other path for this current to flow. So generator current is zero. On the other hand, generator also requires a field winding. So I'm just exactly same thing I'll repeat here. That is an ammeter here and then the field winding of the generator. and then a variable resistance. Now, why this variable resistance? Again, I'd like to be able to control the amount of voltage generated. So if I want to generate more voltage, I have to give a stronger field. Then I am able to generate a higher voltage. We'll see the application of that when we discuss this thing. So now let's call this current as IFG, the field current of the generator. And let's call this current. Now notice the arrow will be upwards because this is the plus minus and this is the plus minus. So the generator is generating electrical output. So current should flow out to the generator. So this is IAG, current in the armature of the generator. Right now IAG is equal to 0 because the switch is open, so there is no current here. We may be generating some voltage, but then the current is 0. Alright, so we have done this kind of connection now. What happens next? First, I had started the motor is running, and then motor is running at certain no load speed, and a generator is connected, and generator is generating some voltage. So what I'll do is I connect a voltmeter here, and then I try to see how much voltage is generated across these 2 points. So you notice this point is actually directly connected to the main supply. So the voltage, so if the main supply is 100 volts or 500 volts, whatever, that voltage directly comes to this end of the switch. Meanwhile, I have to generate that much of voltage here such that both voltages are equal on both sides. So if I generate, let's say 500 volts here, and if I supply also 500 volts, in that case both voltages are same. And how to generate whatever voltage that we want is by changing this resistance. The resistance in the field of the generator, if I increase, then the current will decrease, voltage will decrease. But if the resistance is decreased, then the current will increase and more flux will be there, more EMF will be generated. So that way I can match the whatever voltage. So if this motor is rated at 250 volts, then I apply 250 here, I apply 250, or I generate 250 here, and so on. Now imagine that both voltages are equal, and then I close the switch. So S is closed when the potential difference is 0. So when the potential difference across S is 0, the switch is closed. Now what I'll do, let's denote this current as IA. So let's call this as VM because it will be easier to write it. Now what I can do is, now there is no potential difference, so therefore the current in this loop is also 0. IAG will be still 0 even if I close the switch. IAG is 0 because I am just generating the same voltage. Now how to increase IAG? So what we do is, there are two options. Either I can increase the speed, or I can decrease this resistance and increase the field current. So I have two options of generating more voltage here. So for example, let's say I weaken the field winding here. So I increase this resistance, reduce the field current IFM. That will generate higher speed for the motor. Therefore, more EMF is generated. Therefore, now the EMF is more. The current starts flowing from IAG. That current which is additionally flowing will add to IAM. So if I apply Kirchhoff's current law here, so I'll find IAM, the current in the motor is nothing but IA plus IAG. Or in other words, the total current is nothing but IAM minus IAG. So these two are just applying Kirchhoff's current law at this point. Okay, so now I have the current. So IAG is increasing, IAM also is increasing. So let me write down those relations here. In fact, I'll try to write it here. So what happens is uh, IFM is reduced. Therefore, as a result, what happens? When IFM is reduced, speed increases. So as a result, what happens? Speed increases, EMF induced in the generator increases. So EMF generated increases. Then what happens? IAG increases. So when IAG increases, then IAM also increases. So this way I am loading. So the motor is getting, this means the motor is getting loaded. Motor is loaded. That means some load is falling on the motor, therefore the motor is taking more current. Similarly, generator is also getting loaded. So I am able to load both motor and generator. So by continuing this process, I can increase the load on the motor, I can increase the load on the generator such that in this ammeter I see the rated current in the armature is flowing, then the motor is fully loaded and generator is fully loaded. So this is how the this earlier diagram which I drawn is satisfied. Now, meanwhile, what is the supply that is coming to the armature? So from the mains, I am only taking IA current. So this IA current is only useful for supplying to the losses in the armature. That's all. So let's and of course the losses in the motor. So having understood this expression, let's write some equations and get some understanding further. Having understood the working of this circuit in the previous part of this video, so let's now get down to really calculating what are the losses in this. So now look at this. You see there is this IAM is the current flowing in the armature of the first motor. Therefore, the resistance of this is RA. So IAM square RA will be the copper losses in the motor. Similarly, copper losses in the generator also we know. So total copper losses we know. Now, on the other hand, what is the power that is supplied to the both the armatures? So the power that is coming from the main supplied to both the armatures through this branch is Vm into Ia. So Vm Ia is the total power supplied to both the armatures. So maybe let me write it down. Total power supplied to both armatures combined. So that is nothing but uh, V main into Ia. So that is the total power that is supplied. So of course there is additional supply, additional power is being supplied to the field of the motor and additional power supplied that we are not writing right now. Right now I'm interested only in the middle branch actually. So now what is happening to this total power? So the total power is being supplied to the copper losses in the both windings and the rotational losses in the both machines. So copper losses in both armatures. So this is nothing but IA motor square RA plus IA generator square RA. So this is the total copper loss in the both the armatures. Uh, but this quantity will be more because this there are some rotational losses and iron losses, all these things that are happening inside the motor. So therefore rotational losses of both machines. So, what is the rotational loss includes? It includes the iron loss. So, it includes the iron loss plus friction plus windage losses plus stray losses. Stray loss is another term used for any additional losses that are happening. So, these whole losses will be nothing but this total VM IA minus of this whole thing, IAM square RA plus IAG square RA. So this is the total rotational losses. Now, assuming that the rotational losses are equal in both the machines because both of them are running at the same speed, so rotational losses per machine. So P rotational per machine. So for each machine, P rotation is equal to half of all this. So VMIA minus IAM square RA plus IAG square RA. So I hope this is now clear. Now I got the rotational losses. Now let's look at the generator first, or maybe let's look at the motor first. Change the color. So when you look at the motor, what is the total losses in the motor? Total loss is nothing but rotational losses plus the losses in the shunt field winding. That is the copper loss in the shunt field winding. That is IFM square RF for the motor. So this is the total losses of the motor. And what is the total input to the motor? Total input to the motor is that if I go back here, see the voltage at this point is also nothing but Vm because this point is exactly same as this point. So Vm multiplied by IAM is the total input going into the armature of the motor. Similarly, Vm into IFM is the total input going into the field of the motor. So total input going to the motor is nothing but Vm IAM plus Vm IFM. Now I have input and losses, so therefore I can calculate the efficiency. So let's call it as P motor losses, and let's call this as P motor input. And once I have these two, I can find the efficiency. What is the efficiency? Efficiency is nothing but input minus losses divided by input. So basically output by input. So that is the efficiency. Of course, you can multiply it by 100% to get the value in percentage. So this is about motor. Now let's talk about generator. So what are the losses in the generator? So losses in generator again same P rotational losses. The rotational losses will be there plus the losses in the shunt field. So IF G square RF. So the both motors are identical. So RF is same. So this one is nothing but the total generator losses GL. Similarly, what is the input to the generator? Again, if you refer to the diagram, generator is actually producing output. Okay, so what is the generator producing output? It is producing IAG multiplied by VM because the switch is closed. This point is exactly same equal to this point, which is exactly equal to this point. So the potential of this point is also equal to VM. So and the current direction is leaving this point. So that means the generator's output is that value. From that, locally the generator also consumes some power. If I subtract it, then I'll get the total power output of the generator. I'm sorry, not the input here. We'll have to calculate the output of the generator. So what is the output of the generator? Nothing but Vm multiplied by IgM. This is the power generated IAG, armature current of the generator. This is the total output coming out of the armature, but then minus some power will be consumed by the uh, field. So this will be my power output. So once I know the output power and I know the losses, So PGO, power output of the generator. Now, once I know the losses and output, I can find the efficiency. So how to find the efficiency? So it is nothing but output divided by output plus losses. So just by doing this, we are able to find the efficiency of the generator. So this is the advantage, or this is the kind of mathematical equations behind the Hopkinson's test. So we explained the circuit diagram, and then we had this particular expressions for calculating efficiencies of generator and motor, and this is the thing about this. Let's look at an example problem so we understand better. Solve a problem on Hopkinson's test. The data of the problem is given here, so you can actually pause the video now, go through the question, and then try to solve the problem yourself. Whereas now I'm going to try to solve this problem now. So we begin by just quickly looking at the question. The following test results were obtained while Hopkinson's test was performed on two similar DC shunt machines. Data is as follows. So this is the total line voltage, the main supply voltage, that is 250 volts DC. Now IFM is the field current of the motor, which is 2 amperes. And then IFG is the field current of the generator, is 2.5 amperes. IAG is the armature current of the generator, which is 60 amperes. And then supply current IA is 15 amperes. And each machine resistance is 0.2 ohms. The objective is to calculate the efficiency of the motor and the generator. All right, so let's briefly look at the diagram once again. So this is what is the setup of Hopkinson's test. Now IAG is given as 60 amperes, and then IA is given as 15 amperes. So therefore this current will be 60 plus 15, 75 amperes is what will be the current going through the IAM. So I'll just remove this, and just to indicate I have just written it that way. So let's go back here. Now the first order of business is to find the rotational losses. So rotational losses will be nothing but half of main supply voltage into the armature current given to the both the armatures minus the motor armature current square into RA minus the generator armature current square into RA. So these are the copper losses in both the armatures. This is the total power supplied to both the armatures. Therefore, that gives the rotational losses. So this formula we had written earlier somewhere here. So this one. So this is exactly the same formula I have just taken, and then I'll be calculating this. So let's do this. So half. Now VM is 250 volts and IA is 15 amperes as per the data that is given here. Minus IAM. So the motor's current we just calculated will be 75 amperes multiplied by 0.2. Again minus IAG will be 60 amperes given the question, and again multiplied by 0.2. So this is the calculation we need to do. So let's quickly do that. So what I'll do is first I'll do 75 square multiplied by 0.2. So this is 1125. So minus and minus. Then I'll do 60 square multiplied by 0.2 again. So this is about 720. And this one is 250 into 15. 250 multiplied by 15. 3750. So this whole thing has to be divided by 2. So which is equal to minus 1125 minus 720, everything divided by 2. 952.5. So this is the rotational loss in each machine. So this is what is important. So rotational loss is nothing but it covers the windage losses, it covers the frictional losses, and it covers the iron losses and stray losses. So overall this covers the rotational losses when rotating at the rated speed. Now let's only focus on the motor. So I am looking at only the motor now. Now what are the losses in the motor? So total losses of the motor is nothing but the rotational losses plus the losses in the armature, that is the copper losses, losses in the armature and the field winding. So IA motor square RA plus the field winding, that is IF motor square into RF. So instead of this, I can also write VM into IF. So like this. So this covers the total losses occurring only in the motor. So the rotational losses are 952.5, already we have calculated. Copper losses in the armature are 75 square into 0.2 plus, and what is this one? This is the copper losses in the field winding. So this is again 250 volts, and the field current I recollect is 2 amperes. Let me check it. Yes, 2 amperes. So this is the total losses that are occurring in the machine. So what is the total loss? So we all know this is, let's calculate that, 75 square multiplied by 0.2 is this one, plus 250 into 2 is 500 plus 952.5, 2577.5. So this is the total losses that are occurring in the motor. Now what is the input to the motor? So the input to the motor is nothing but VM and then the field current of the motor plus the armature current of the motor. So this is what is ultimately going into the motor. So we can see voltage into current is power. So this is the VM into the first term will be the power going into the shunt field winding, and this is the power going into the armature field winding. So 250 volts multiplied by the field current is 2 amperes and then the motor armature current is 75 amperes. So this will be 250 into 77. So 2, 250 multiplied by 77. 19250. So 19,250 watts is the input. Now I have the input and losses, so I can find the efficiency. Efficiency is nothing but input minus losses, that is 19250 minus losses, that is 2577.5 whole divided by input 19250. So this I'll convert into percentage. So from this I subtract 2577.5 and then from that I divide 19250. So I'm getting 86.61 as the losses, as the efficiency of the motor. So this is one part of the question. Now let's continue and now we'll take up the generator. Now again, what are the losses in the generator? Total losses in the generator is nothing but the rotational losses plus the copper losses in the armature. So IAG square RA plus the copper losses in the shunt field winding, VM into IG IFG, field current of the generator. Now the rotational losses are same for both. That's what we had. That's why we divided by 2. 952.5. So this is 952.5 plus the generator current is already given in the question, 60 amperes into 0.2 plus the 250 volts, and the generator field current was given as 2.5 amperes. So we have all the numbers now. So let's again do this calculation. So 60 into 60 into 0.2 is the middle term. To this I will add with brackets 250 into 2.5. Then to that I'll add 952.5. I'm getting 2297.5 as the total losses. So I have the total losses. Now what is the total output of the generator? So for the generator we talk in terms of output. The total power output of the generator is nothing but the power generated, that is Vm into IAG is the power generated. From that I subtract the losses of the shunt field winding. So that is Vm into IFG. So or in other words Vm into IAG minus IFG. So that is nothing but 250 multiplied by 60 amperes minus the field current is 2.5 amperes. So this is the total output. So I'm running out of space, so I'll just cramping a little bit. So this is 60 minus 2.5 multiplied by 250. 60 minus 2.5 multiplied by 250. So 14375. So 14375 watts is the output of the generator. Now I know the losses and I know the output, so I can find the efficiency of the generator. So that is nothing but 14375 divided by 14375 plus the losses, that is 2297.5. So this is nothing but, so this is divided by the total input. So I'm getting 86.22%. So this way we are able to get the efficiencies of both the motor and generator for this problem. So I hope you learned something about this particular by solving this particular example problem. So let me conclude this by briefly stating what are the advantages of Hopkins' test and what are the disadvantages of Hopkins' test. So we have discussed Hopkins' test here. So the advantages are two machines are tested and these two machines are under the loaded conditions. They are not like no load test where you are just doing you are estimating under loaded conditions what will happen, but we are actually loading. So actually the full current is flowing in IM and full current is flowing in IG and so on. So the effective of loading the machine comes into picture. So that's a advantage. And another advantage is that whatever we take from this main supply is only the current for supplying the losses of the entire experiment in both the machines. We are only supplying the losses. So that is another advantage. So I can, whereas the disadvantages are, the thing is although the both motors are loaded, they are not loaded to the equal level. So that's why you see slight variation in the efficiency of both the machines. So that's just a small thing that we need to consider. So that effect will be more severe for smaller capacity machines. So therefore Hopkins' test is more suitable for testing of large DC machines. So with that I'll conclude this topic of Hopkins' test in particular and in general the testing of DC machines. Hope you have learned something from all these things. Please do like and share my videos. Thank you.